So this is the second part of chapter 6, talking about the properties of dry gases, and this part I'm going to talk about the viscosity of dry gas. So we're going to see some correlations about how to calculate dry gas if you have some of the inputs. For example, figure 6.6 of here shows the viscosity of ethane, C1, C2, and based on the temperature and also based on the pressure. So if you have the temperature, and if you have the temperature, oops, okay. So if you have temperature in horizontal axis, and if you have the pressure, you should be able to read viscosity in micro poises, micropoises. Okay. Figure 6.7 shows the viscosity of gases at atmospheric pressure. So if you have the temperature, okay, and depending on the type of gas that you have, let's say this is helium, air, nitrogen, and these are N-heptane, N-butane, and this is methane. So as the gas getting heavier, the viscosity decreases. So for example, for methane, at different temperature, here you could read the viscosity. So this is viscosity at atmospheric pressure. So pay attention to this. Okay. And if you have viscosity at atmospheric pressure, later on you should be able to calculate the viscosity at the certain pressure. So what happens if you have a mixture of gases? If you have a mixture of gases, we use a mixing rule. This mixing rule proposed by the equation 616 shows the you use the composition of gas, Y, and use the molecular weight of the gas. So it's the sigma viscosity of component multiplied by the composition multiplied the molecular weight divided by this is and also square root of the molecular weight. So we're using these mixing rules to calculate the viscosity of gas mixture. So after figuring out the composition and the molecular weight for each component, we use the correlation in the previous figures to figure 6.7 to estimate the viscosity of each component, and then we're using this mixing rule to calculate the viscosity. Example 6.9 is example 6.9 is calculating the viscosity of gas mixture given below at 200 degrees of Fahrenheit and pressure of 1 atmosphere absolute. So we have 4 components: methane, ethane, propane, and N-butane. We have the composition. So what we need to do is, so this is Y. What we need to do is calculating the viscosity from for each component using the figure that we have in previous here, figure 6.7. Okay, and then using the mixing rule that we have here to calculate the viscosity of the mixture. Okay, so we'll read the molecular weights from the appendix A1, page 492. Read the viscosity from figure 6.7, and again this is atmospheric pressure, and then we apply the formula. So things straightforward. Okay, and so it's always good to create a table like this. The given part is here. We'll read this from appendix 1. the molecular weights, and then we have to calculate the square root of the molecular weights, multiply by the composition. We'll read the viscosity at atmospheric pressure for each component from figure 6-7, and then we calculate this function, and eventually we need to calculate the sigma of these two. Okay. So what happens if the composition is unknown? Okay. If the composition is unknown, we have another correlation. For atmospheric pressure, we use a figure 6-8 that based on the molecular weight of the gas could calculate the viscosity at 1 atmosphere. Okay. So it's a straightforward molecular weight or gas-specific gravity, and we calculate the viscosity. So again, if you remember from the previous chapter, if we had non-hydrocarbon components like hydrogen sulfide or nitrogen or carbon dioxide, we had to correct the Z factor. Here we have to correct the viscosity if we have those non-hydrocarbon. And the reason is, looking at this figure 6-7, you see the helium, air, nitrogen, carbon dioxide, and hydrogen sulfide. They have a totally different high viscosity compared to the hydrocarbon values. So we have to make sure that we correct those values using these formulas. So if you have a mole percentage of this non-hydrocarbon, and if you have the gas viscosity, basically you go here and you read the value of the viscosity. So this correction added to the viscosity, so increases the viscosity that we are reading from the previous step. So again, you measure the gas viscosity using the previous correlation, figure 6-8, and by knowing the percentage of the non-hydrocarbon value, for example, for H2S, nitrogen, or CO2, you go read the amount of viscosity that you have to add to the value of the viscosity that you have. So this is the correction that we have. Example 610 is using figure 6-8 to rework the example 6-9. In example 6-9, what we had 4 components. We had the composition, and we create a table using the mixing rule and calculate the viscosity. Okay, so if we have the molecular weight that we could calculate it from these values, we should be able to calculate it from figure 6-8. So by having the molecular weight, we should be able to calculate the viscosity at atmospheric pressure. So far we measured viscosity using the correlation at atmospheric pressure. What happens in reality, the reservoir condition has much higher pressure than atmospheric pressure. Therefore, we have to calculate the viscosity at those pressure. There's a specific correlation, figure 6-9. And by the way, the equation behind these correlation are in the appendix and appendices at the end of your book. So you could see the equation and create the Excel sheet if you are interested. If you have the pseudo-reduced temperature and pseudo-reduced pressure, which you already learned about this, how to calculate them from chapter 3 using the Z factor. You calculate the pseudo-reduced pressure and temperature using the pseudo-critical pressure and temperature and the reservoir temperature and pressure, and you should be able to calculate the viscosity ratio. What is viscosity ratio? Viscosity ratio is the viscosity at a certain pressure divided by viscosity at atmospheric pressure. So if you read the viscosity ratio here and calculate the viscosity ratio at atmospheric pressure, you should be able to calculate the viscosity at any pressure. Okay. So viscosity of gas at high pressure using 4 figures 6, 9, 6, 10, 6, 11, 6, 12. Again, you determine the viscosity at 1 atmospheric pressure, calculate the pseudo-reduced temperature and pressure values, and select the right figure based on the specific gravity value. These figures are sorted based on the specific gravity, and they read the ratio, viscosity ratio from the chart, and then since you have the viscosity at atmospheric pressure, you should be able to calculate the viscosity value, which is the ratio multiplied by the viscosity at atmospheric pressure. So the difference between 6.9, 6.10, 6.11, and 6.12 figures are the range of the specific gravity. For example, for 6.12, the range is from 1.5 to 1.7. Example 6.11, calculate the value of viscosity for the dry gas of example 6.3. So just going back to example 6.3. Value of formation volume. This example gives you a specific gravity of 0.818 at the temperature 220 and 2100 psi. So you have to use the specific gravity of 0.818. Okay, so again, last week we didn't have any class, and today, because of the weather, we didn't have class. So I hope that the recap helped you, and also about the viscosity part of chapter 6. These are assignment. You had the deadline was yesterday, and I was hoping to go over the assignment today, but we couldn't make it. Send me your questions via email, and I'm gonna upload this right away and send it, post it on Blackboard. All right, stay safe out there, have fun, and do the homework. Bye bye.